detect the attack using the tiny digital twin. I'm working with Marjan at Mälardalen University and also Sarah. And this presentation is based on our two papers that recently published. The first paper is actor-based modeling of the attacks and how we doing the security analysis at design time. And the second paper is doing the monitoring the cyber physical system at runtime and how we catch the attack actually when the system is operating. First, I start from the cyber physical system. I explain how this system works and what is the component of these kind of systems and some examples. And then I go to the method, how we generate our tiny digital twin and how we use it at runtime. And for giving the detail of our method, I using our two case studies. We developed these monitoring and the attack detection for these two case studies to be more understandable for the listener or audience. And finally, I give an overview of our results and what we want to do for as a future works. Okay, cyber physical systems are integration of the software components in the cyber layer and the physical component in the physical layer. That these software components that are doing the computation work based on what the sensing data coming from the sensors and make decision based on that data and deliver some kind of the commands to the actuators to control these physical processes in the physical layer. Example of these systems are transportations, robotics, or production systems that deliver the product or service. And due to the openness of this system and usually using the wireless channels for the communication between the component, this cyber layer may be vulnerable to different kind of the attacks. Here we consider that those attacks that inject the code to the controllers or inject a malicious packet in the communication layer between these components. So attack on the communication and attacks on the components. These attacks may lead to some safety violation in the physical layer. These, for example, for this example, maybe the crashes or misbehavior in the production or services. One of the challenges for the security domains is that they are usually using the intrusion detection for identifying the attacks or detect the attacks. But for the rule-based IDS or intrusion detection system, developing and writing rules is so difficult. And the security and safety engineers try to write the well policies or rules to catch more attack or identify what is the right behavior in the system and the misbehavior or anomalies in the system. So based on that, we take this goal as attack detection and prevention in the cyber physical system. We do the runtime monitoring by using the tiny digital twin. This tiny digital twin is a formal model, is the abstract behavior of the model that generated by formal methods, specifically doing the model checking of the one actor model. And then later I will explain what is the actor model here. And the result of our work that makes the attack detection process simple and systematic for the safety and security engineers. And by using this method and the module we develop, they can catch the attack and also get some concrete trackable reports that shows what is the source of the attacks happen in the system. The idea is that we develop the one monitoring module that is placed in the field layer in the cyber physical systems where the controllers receive the data from the sensors and send the output commands to the actuators. These monitor modules have a one model inside itself that follow the behavior based on this model. And if we find or observe that some packets are not following this behavior specified by the model, it's considered that these kind of the packets or the sending receiving data as a malicious one and consider them as an attack. And when these mismatch or inconsistency happen in the system, the monitor module provides reports that show what is the different behavior in the system or what's the source of the attacks in the system. The reason for this detection is that anything is not related to the requirement, especially safety and security requirements, we consider those behavior as attacks. To build this system, the monitor and the tiny digital twin, we follow 3 steps. At the first step, we perform model checking. We develop the one model in the Rebeca language that we call it Rebeca code, and doing the model checking by specifying the requirement in the CTL or LTL or any logic languages, and generate one state space. This state space is an attack-free model that shows the whole correct behavior of the system. And after that, we perform one reduction and abstraction based on the observable sending and receiving the packets or the messages. Because the monitor is placed in the field layer and just see the some packets, not the whole messages sent and received in the components. So this state space will be reduced or will be abstracted based on the observable data for the monitor. And finally, by this abstraction tool, we generated one tiny twin that we call it tiny digital twin because it's abstracted, and we place it in the one monitor. We generate or produce this monitor with the LF compiler. This is the compiler for the lingua franca language, specifically developed for programming cyber physical systems. And this language enable us to synchronize the time is defined in the model and the actual time that is a clock time in the system. We evaluate our method and attack detection system in different case study. Here I show the 3 case studies. The first case study is secure water treatment system that is responsible to produce the clean water. The second case study is pneumatic system that some cylinders pick and place different objects in different positions. And the third case study is a temperature control system that regulates the temperature inside the room. For this presentation, I use the first and third case study to explain the detail of our method. The first step is about model checking. We use the Rebeca modeling language, that is the actor-based modeling language is developed for specifying the concurrent execution and also distributed systems. This language has one embedded model checker called AFRA that has the IDE that easily we can write the model in this IDE and also the properties and doing the model checking and see the result. The website, the Rebeca homepage, show different projects that are successful by using this AFRA model checker. AFRA and also the Rebeca and LF, lingua franca, all is about actors. Actors are entities that send and receive messages, and by this behavior, we can specify the system. We model the communication by message passing, and we model computations by taking the message and handling them. For example, here we have the one actor that it has a message servers, a state variables, and the queue that store the coming messages. And this actor want to send the two messages to actor 2. The actor 2 have a two message server A and B. When these messages are arrived to the queue of the actor 2, the responsible message servers take the messages from the queue and handle it. By this technique, we specify the old component of the system as actors and also the computation and communication in the system. For the first case study, it's a water treatment system, that there are different components here: water tank, PLC in the PLC cabinet, and the valve and pumps that help to circulate the water in the different tanks and produce a clean water. We have a PLC that receive the sensing data from the wireless sensors that show the level of the water in each tank. And these PLCs sending the command open or close a valve or turn on or off the pumps to the actuators here, valves and pumps. But due to the wireless channel here and using the simple password-based authentication technique, this system may vulnerable to injection attacks or false sensor data injection or faulty control commands in the communication channel. And these attacks may cause a damage like water tanks overflow or underflow. So in order to check this design and identify the vulnerabilities and also attacks, we perform the model checking. For performing model checking, we are building the one actor model. This actor model is built from the system specification. First, we draw an abstract architecture of the system. For this system, it's a three stages that when the raw water is coming to the tank 1 and then going to the tank 2 and then tank 3 and clean water is produced here. We specify each component of this system by the actors. Here are the PLC1, PLC2, and PLC3 are actors, and also these control messages by the message passing between these actors. And for performing security analysis, we focus on those input and output, and also those components maybe are vulnerable to the attacks. Here, the red cycle shows the vulnerable channel or the wireless channel, and the blue cycle shows which component could be damaged by the attackers. And to perform and build the one attack model over this system model, we have three schemes. Scheme A shows that how we generate a one actor as a malicious actors and inject the malicious messages between the actors. Here is the attack on the communications. And scheme B is the attack on the component. We specify the one component that behave maliciously, have a malfunction in the different time. And the scheme C is the combination of the attack in the scheme A and scheme B. And we combine these attack on the component and the communication to see what complex attacks can happen in the system. Actually, these attacks and scenario violate the security objective. To categorize these attacks, we use the stride threat modeling as a reference and put these attack scenario with respect to the security objectives are defined in the stride threat modeling. For this case study, we developed the injection attack that's inject the malicious data in the communication and also over the components to see how what kind of the vulnerabilities we can find at the design time. We have the develop code here. This is the develop code for the SWAT or water treatment system. The all components are defined as actors. Here we call it reactive classes, and also the logic of the component and how they are behaving are modeled or developed by the message servers. And we define the properties here as assertion that shows the water overflow or underflow for each tank. We involve one attack model here to perform an injection attack between the communication messages between the components or actors. Here we define the one attacker actor. These attacker actors perform the attacks at a different channel or communication channel, malicious message and attack time. So by this way, we involve the attacker to the model and perform a model checking. And when this attacker is able to fail the system by the specific behavior, the model checker shows the one counter example and show how these point of the attack is happening and how this property is failed. And when we fix the model and have an attack-free model, we use this state space that is free of the attack for the next phase, that is runtime, actually runtime verification. At the design phase, by doing these security analysis, we found that this system, which component could be activated and which security violation will be happen. We perform 100 attack scenario on the communication and 84 attack scenario on the component and more than 8,000 combination of this attack. And finally, we found that the 29 cases that successfully violate the system safety requirement. For example, in this table, when the system is operating and is a state S0, and when this component is doing as a malicious one and is as a compromised component, and the pump is turned off, and at the same time when this injection happen between the PLC 1 and the valve, this tank 1 will be underflow. Sorry. And the second step is about the abstraction. We get this state space free of attack-free model and the list of the observable action we would like to have it in the abstract model and perform this abstraction process over this state space. We preserve the whole state transition in this abstract version by keeping or preserving the branching by simulation. And for this system, for this case study, we use the list of the sensing action, open and close and on-off actions, and we perform abstraction on this state space model and generate this tiny digital twin. The original state space includes the 900 states and 1,000 transition, but this abstract version by keeping these observable action will be 86 state and 100 transitions. And then we need to generate one software module to be used in the system. We use the lingua franca as a programming language for building this monitor. This language is meta language, and body of the LF language is written in the C or C++ or Python languages, and then we by doing that we synchronize the the time is defined in the model, and the time is shown in the clock of the system. Yeah, and the reason we use this LF language is that both languages, LF and Rebeca, have a same semantic. Both are actor-based languages, and it is easy to develop the code in the Rebeca and then mapping these Rebeca model to the LF language. The actors in the Rebeca is in reactive classes, and the actor in the LF are reactor, and the rules in the Rebeca language are defined as a message servers, and those are coming in the LF language by reactions. So by compiling using LF compiler, we generated one executable code. Here we developed the code for these cases study by in the C++ language. This is a short video that we simulated with in LF, that the 3 PLCs are here, and the listening is waiting to get the sensing data from the sensors, and the monitor is placed in the middle. And by getting the sensing data and also the inside tiny digital twin, decide if the malicious data is transmitted to the PLC or not. And this module is developed for injecting attacks or malicious data into the system, and to evaluate if the monitor is correctly detected these attacks or not. The second case study, the temperature control system. Is the cyber physical system actually, and there's a controller here and sensor, and one HC unit that's responsible to heating or cooling this environment inside the room. The same as the SWAT system or water treatment system, the wireless communication channel may be vulnerable to the attacks, and by performing attacks, we may have a degradation of the process, temperature regulation process, or pushing the temperature value out of the defined range. So we perform the model checking and do the abstraction. For this system, we keep the time value and also the sensing data and activation, the heating and cooling process, and also switch off as observable actions in this system, and we make the other actions as a tau transition in the system, and generated these tiny digital twin to be kept in the monitor to perform a runtime verification. Before seeing the monitor, here is explaining how the abstraction process is work on the state transition system or original state space. This is some part of the state space generated for the temperature control system. We perform a BFS graph search over this state transition system and find the equivalent state based on the given list of the actions. And merge those equivalent state to generate the equivalent classes. During this search, we're keeping the observable data and hide those transition are not provided in the given list as a tau transition. And this method or this algorithm is preserve the trace equivalence and also branching time equivalence between the original state space and time then reduced state space. This way help us to keep those properties are validated or verified in the original state space, and also are preserved in abstract version. And this is a mapping between these Rebeca code and LF for temperature control system. We have one visualized graph when we are generating the monitor and the system in LF language. This is a monitor is generated in LF for the temperature control system, and we load the tiny twin in this monitor. And We place the monitor between the controller and the HC unit here to observe the messages and take decision if these messages are matching with the transition in the tiny digital twin or not. And here, this is a part of the tiny digital twin for the temperature control system. And we want to show that how the attack scenario will happen on the system and in temperature control system, and how the monitor can catch this attack. Assume that system is performing and reaches this state. And at this state, the attacker injected false sensor data 21. And because the next state after this state transition, there is no state that show the 21 degrees happening in the next state. These behavior considered as an attack, and the monitor stopped the execution. And because these messages reached to the controller, and controller made the wrong decision and send the false activate H here, the wrong command, the monitor dropped this command as a faulty command and stopped to system to execute further. But for example, here we have some kind of attack that mislead the system by in different branches. For example, assuming that the system is executing in this state, and we have the right branch here, 24, but the malicious attacker send the 23 to the system. This attack will not catch by this model, but will be catched but by adding the meta rules over the branches on this model. We will annotate that these meta rules that will come from the engineers or some we will use a machine learning technique to add these data to the branches to take them valid decision when this kind of attack happening on the system. Yes, this is a result for the temperature control system. That's we perform 20 false sensor data and 12 faulty control commands, and also the combination of these attacks, we perform 240 coordinated attacks. And by this evaluation, we found that the detection rate for this system is around 68%. And by performing each attack scenario, we found that which attack with which value can fail the system, for example, which sensor data or which control command, and which one are not detected by these monitor module. And those attacks are detected by the monitor. We provide a valuable report that show at which time with which false value these attack is happened. For the future work, we would like to have a adaptation technique to update our tiny digital twin at runtime and with respect to the system changes. And also we would like to have a mitigation plan to recover the system after attack. And by using the machine learning, we want to improve the detection rate of this monitor, and also how we can extend this work to monitor the system, actually the distributed system in the large system, for example, in a robotic system, and how we can use backtracking technique to show the exact source of the attack in the source code of the develop of the system. Yeah, thank you so much.